Good morning, good afternoon, everyone. My name is Harsha, and today I'll talk to you about nonlinear system identification and model predictive control of AUVs. Uh, this is partly based on a workshop we did at Croatia last month with Chris, and I'll be going a little more in detail since this audience is a little more advanced than the audience represented. So I'll start with the background on why we need to use system identification, and then I'll describe how we can perform system identification using physics-informed learning. Then I'll talk about how we can use these identified models in adaptive model predictive control. And finally, I'll talk about augmentations and next steps to how to get this to actually work on a real vehicle and in a real world scenario. So AUVs such as SAM, Lolo, and Hugin, which we are familiar with, can perform new tasks in challenging environments. We've been trying to make them perform these tasks. It doesn't always work, but that's our aim, right? For example, to do under ice mapping or in glacier fronts in really risky environments, or to do inspections in algae farms. We've been trying that last summer. Or pollutant cloud tracking, where maybe a swarm of AUVs is trying to track a big pollutant cloud. Now, when you do these things, you have high requirements on sensing, control, and navigation, and you also have significant risk and uncertainty and disturbance. So how can we consolidate all this together and balance these different requirements and still have good performance? That's a good question, right? So when you think about that, one piece that's common to all of them is to have reliable dynamics models. These are important for sensing, they're important for navigation, they're also important in control. However, if you consider an AUV like SAM, the dynamics can be highly nonlinear. If you consider agile maneuvering, or if you have high disturbances as well, you could have turbulent flow in the body. And when you have turbulent flow or transitional flow, you can see the figure here that you have different kinds of vortex shedding, and this is very hard to physically model with equations. In this case, learning from real world data can be beneficial so that we can capture such nonlinear effects. On top of that, we have another challenge. SAM is an underactuated AUV. It's hydrobatic, which means that it is very agile and it has a really interesting actuator configuration that makes it perform really cool maneuvers. You can do interesting things with it, but to make it do those things is more difficult because to get good control strategies in this kind of underactuated system is challenging. So we have this two problems on one side of having a complex model, and on the other side, having very few controls. So how do we reconcile both of these differences? Here, we can consider system identification. So with system identification, we can learn a model of a dynamic system from measurements. So therefore, we can use data and learn a model from it. If we can periodically update the model based on new measurements and put this into our controllers, we can get adaptive control, or if we use it in estimation, we can get adaptive estimation as well. So we get two key benefits. On one side, nonlinear effects such as turbulence can be better captured. And on the other side, if we have more accurate prediction models, we can get more effective control or also more effective navigation with good state estimation. So the workflow for this, we can begin with some data generation. So at the simplest level, as a toy problem, which is what I'm going to present today, we can use an analytical equation of motion related model based on Fossen's equations, for example. Or you could use a simulation environment to generate data, or you can use real world mission data. With this, you can get its state versus action data, and then you can learn a model. Then you have to identify a system. Basically, if you have some states and inputs, you want to get what is this x dot equal to f of x comma u. And you could do that doing physics-informed learning, or at a simpler level, you could just do linear regression. Or if you want to go really crazy, you can use some newer techniques such as Lagrangian neural networks. And once you've learned the model, what do you do with it? First step, you could simulate your system. You could get a better simulation model of your system, which is more realistic. You could use it for control, which I'll talk about moving forward, for model predictive control, for example. And you could also use it for state estimation to update a prediction model there. So what do we mean by physics-informed learning? So in one thing, machine learning allows us to learn nonlinear representations of data. In an AUV, in the dynamics, the damping effects in particular are highly nonlinear, and they're nonlinear with respect to velocity. So we can create a model that learns these nonlinear terms of damping using a neural network while using the equations of motion for the rest of the system. So it's a form of gray box model where you have you know the physics of most of your system, but you have your neural network that learns the nonlinear effects. Doing this, you're able to learn these effects while still being informed with the laws of physics with the rest of the model. And in this way, you don't go completely crazy by not knowing what's happening inside your neural network, but you know that it will still follow Newton's second law of motion, but there's only some parameters that are going to change with time. This gives you a little more security when you want to learn from data. So I collaborated with Chris on this project, and then we generated measurement data using an analytical dynamics model using Fossen's representation. And then we used a tool called JAX, which allows us to do high performance automatic differentiation. And we trained a neural network to learn just the damping terms in Fossen's model. And then we compared this learned model with random initial and final conditions with the analytical model. So if you look at the training, we trained the neural network until it came to a reasonable level of loss function. And then we compared the analytical and the learned models. So the solid lines are the analytical models, starting from random initial conditions with random control. And we apply the same initial condition and the same control to the learned model. And you can see that they almost overlap. They're very close to each other. So with this, for a toy example, in the sense that by writing out the equations of motion and trying to learn the system, we're able to do that using this method. But what do we do once we have identified the model? We can use it for several things, like I said. If you're doing control, you can have a more accurate prediction model for optimal control, because there you can use a model of your system and try to solve for it. You could also perform real-time simulation. I have a paper on that before, which I presented in the past seminar. But you could improve on your prediction model in the simulator using these kind of systems. And you could also, if you're working with navigation, maybe have better prediction models for your Kalman filters. So there are several possibilities that you can do. I'm going to focus a bit more on the control side. So Ozer showed this really nice flowchart about the whole control and planning system on SAM or also on Rolo. Here I'm showing a subset of it. So if we have our system of the AUV, in order to control this underactuated system, we start with the behavior tree for supervisory control, which goes to a motion planner, which provides control objectives and constraints to a controller. From the actual system, our sensors give us sensor feedback, which are a form of measurement. So what I want to do is I want to do system identification to learn a model from this data and to update a model inside the controller so that we can have adaptive control. So I'm going to focus on this box here. So we're going to consider model predictive control. In MPC, we reframe the control problem as an optimization problem. We have the following objective, where we're trying to minimize deviation from a reference trajectory while using minimum control inputs. And we have a constraint, which is the dynamics of the system. And putting this together, we use a solver such as quadratic programming or convex optimization to solve this optimization problem. And we do this for a set prediction horizon, and we repeat. So this is model predictive control. And in this method, you can get good results if you have a good model of the system. So if we can identify a nice model of the system, we can also get nice control. So there's a nice trade-off here, right? So to implement this, we can use that learned dynamics model that I just presented and put that into linear time varying MPC. And then we can send AUV from 0, 0, 0 from the origin to a waypoint in 3 dimensions. To do that, we linearize the nonlinear model at every time step. And then we solve a quadratic program. That's a form of optimization problem. And then by solving this quadratic program, we find the optimal control over a certain prediction horizon. And to do all of this, we use this library called CBX, which performs convex optimization. So by doing this, you can see here that in this, using that same model, I have simulated that model to go from 0, 0, 0 to a position, I think, 5, 0, and 5, I think. And in order to do this, you start from, you first use the propellers to a certain extent, and then after that it stops, and then it goes and uses it slows down because it already got a particular velocity, and then it uses its rudders in order to orient itself to reach that position. And what you notice here is that these bang bang features, which means which is quite common for optimal solutions in that sense. So the end result here is that using MPC, you can actually control the robot to reach this target. This is in simulation. but we can use MPC to do it. And the model that we've used here, both to simulate it as well as in the controller, was this learned model that we learned using neural network. So you can try all of this yourself. We presented this in Croatia at Breaking the Surface. There's a Colab notebook if you follow this link. I think later when this is uploaded to YouTube, we can share this link here, or just after this talk, I can share it in the chat as well. You can do it yourself. You can try all of these things. You don't have to install anything. If you just log in, you can play it on your browser, and you can try it yourself. That's it. And I think some of us here, there's some familiar faces here as well. So there's Joanna, Josephine, Chris, Ivan, John. And then this was for an analytical model of an AUV. So we've written out the equations of motion, and I've shown you something quite simple, what we have already made work. But now we need to augment it. How can we use field test data in system identification? Then it's actually realistic that we could use it on an AUV. Also, we might want to learn conservative forces and equations. So we don't just want to learn the damping terms, but maybe we also want to learn Newton's second law of motion. If you want to put this together in real time, so in this case, you have to train the neural network in order to learn the model, and then you can use that learned model. It doesn't like instantly update the model at every time instant. So how can you real time identify such a system? And finally, the MPC that I showed was this time varying linear MPC. We could use nonlinear model predictive control to do some of these tasks. And I've been addressing all of these to some extent at the moment. So looking at field tests to gather more data, we're going to Christianaberry in a couple of weeks to do tests on the algae farm, but also to get some data for system identification. I'm going to be doing some experiments for MPC for hydrobatics in a control environment. We have not yet decided on the exact date, but we're planning in early December. And we want to do some control as well as collect data for system identification. And we have the field station now in Duro near Stockholm, and we can do regular testing there. So I hope to get a lot more data which we can use in order to learn better models. Then if you want to learn conservative forces, right? What we presented was a gray box model. And we wrote out the conservation of energy as Newton's second law. However, there is a method called Lagrangian neural networks where we can learn these Lagrangians, and then we can derive the conservative forces using Euler-Lagrange equations. In that case, we can have a black box model where we can have all the forces can be represented by the conservative forces, the non-conservative forces, and the control forces. Right now, we have only the non-conservative forces which I've learned, but we want to learn all three perhaps with constraints. There's a master thesis student who was working on this, Badi, but we still have to build on his work to make it work with real data or with more complex systems. I've been looking at real-time identification. So if you want to identify the system immediately, like instantly, as soon as you get some data in, you can use sparse regression. So here you want to do some linear regression. You don't want to do something too complex because you want it to work quickly. So using sparse least squares regression, you can rapidly identify nonlinear systems. There's one algorithm called SINDY, where you create a sparse or parsimonious approximation of a nonlinear system. So here, if you have a nonlinear function, for example, the dynamics of a robot or a pendulum, you can have a library of nonlinear functions and coefficients for that library. So it's like a matrix product. And then you try to regress the coefficients when you know what these functions are. And by doing this, you can do it very quickly. I've tried it out for a double pendulum case, and it works pretty well for some initial conditions. And the authors of this algorithm, they claim it works also for chaotic systems. So I think it has promise for AUVs, and I want to try that out. I think this can be very useful for adaptive MPC because then you can instantly update your model like every 10 seconds or something like that. Looking deeper into model predictive control, Chariklia did her master thesis with me, and she did a really good job in improving our hydrobatic simulator to integrate nonlinear MPC there. So now we have a comprehensive test bed to design nonlinear controllers, especially model predictive control. We can switch between different controllers very easily. We can simulate disturbances, and also it's very tightly integrated with ROS. We can publish and subscribe to ROS topics. We can also generate C code and deploy it onto hardware. So this whole ecosystem, I think we're very excited to actually use it and test it out in the field somehow. So here are a couple of results actually what Chariklia generated. So using MPC in the simulator, you can make it hold like a going straight or going straight vertically as well. Just takes a few seconds to run. Might crash, hopefully not. Yeah, that. Oh, sorry. Let's go back. How am I on time? Okay. That's good. Yeah, so as you can see here, it's using, I think, nonlinear MPC in order to go up to a certain waypoint on its own. And this whole thing works on Simulink, but it also runs with ROS and everything else on it. So it publishes to a ROS topic, and then the AUV subscribes to a ROS topic and moves around. And it holds, as you can see from the plots, it does hold the position. So to conclude, physics-informed learning is an interesting topic which can be used to learn the dynamics model of an AUV from measurements. It can be beneficial, especially for learning nonlinear effects that are difficult to model. So I think that especially for these really difficult to model behavior, it's relatively easy to get this to work. The learned model can be used for adaptive MPC. That means hopefully we can get better controllers that work better in difficult environments. And right now I'm working hard on augmentations to demonstrate this on an actual AUV. So that's a priority at the moment. And I've been very excited to work on this area. And if anybody wants to talk more on this area, I'm happy to talk. And thanks for listening.
Yes. I can shout. Yes.